Welcome to part 2 on the monoid structure of the power set of a group. If you haven't already watched part 1, I recommend that you do so. But in summary, last time we defined the power set of a group G, we defined a monoid, and we showed that the power set of a group G inherits a monoid structure naturally from the group structure of G. More precisely, if G is a group and HK are subsets of our group G, we defined H star K to be the product of H and K as subsets of G. We then showed that under this operation star, the power set of the group G is a monoid. This time, we will show that the set of all normal subgroups of a group G is a commutative submonoid of this power set monoid. First, let's define a submonoid of a monoid. If M is a monoid with binary operation star and N is a subset of M, we say that N is a submonoid of M if N is closed under star. This means that if K and N are elements of the subset N, then K star N will always be an element of N. And that the identity element 1M of the monoid M is contained in the subset N. Intuitively, what this says is it says that the subset N is a monoid in its own right. We say that a monoid M is commutative if x star y equals y star x for all x and y in M. Let N of G denote the set of all normal subgroups of G. We claim that N of G is a commutative submonoid of the power set monoid of G that we defined before. To show this, let K and N be arbitrary elements of N of G. So K and N are normal subgroups of our group G. To show this closure condition in N of G, we need to show that Kn is a normal subgroup of G. To do this, let X be an arbitrary element of our group G, let K be an arbitrary element of our normal subgroup K, and let N be an arbitrary element of our normal subgroup N. Then, to show that Kn is a normal subgroup of G, it suffices to show, from the definition of a normal subgroup, that the element xknx inverse is in Kn. xknx inverse equals xkx inverse x nx inverse. Here, we've inserted an identity element in between K and N and expanded it as x inverse x. Now, grouping these three elements of G together and these three together, we get that this expression is equal to xkx inverse multiplied by xnx inverse. As K is a normal subgroup of G, that just says that this element here is in K, and likewise that this element is in the normal subgroup N. So this product is contained in Kn, and we've established closure. Now note that the trivial subgroup of G is normal in G. This says that the identity element of the power set monoid of G is contained in the collection of normal subgroups of G. So with these two conditions valid, we've shown that the collection of all normal subgroups of G forms a submonoid of the power set monoid of G. It remains to show that it is a commutative submonoid. To do that, we just need to show that Kn equals Nk. Kn is the union of these right cosets of K in G. Now, recall that because K is a normal subgroup of G, that just means that any right coset of K in G will coincide with its corresponding left coset. So we have that this union of right cosets equals this union of left cosets. But this union here is precisely Nk. So we've established that the collection of all normal subgroups of G forms a commutative submonoid of the power set monoid of G.